So I'm excited to present our research on flexibility provision in the Swiss energy system that covers power, hydrogen, and methane infrastructure. Okay, so already today, Switzerland has a seasonal mismatch between domestic power generation and demand. And this mismatch today is mainly addressed via hydropower and power trade. Okay, but in the future, this seasonality will even increase. We have the electrification of heating and mobility, which increase the demand in winter. At the same time, we have the nuclear phase out and increasing penetration of PV, which increases the need for flexibility across time scales. So there are various flexible resources that Switzerland can use to meet this increasing flexibility demand. The first one is storage. So although reservoir storage is almost already depleted in Switzerland, but there is potential for fuel storage and also batteries. The next flexibility option regards to renewables like alpine PV and wind, which have a very good generation portfolio in winter. We have the option of sector flexibility or sector coupling. So in this regard, we mainly look at power generation from gaseous fuels and also power to gas. Sector coupling in general is crucial to meet the emission targets by decarbonizing mobility and heating. In addition to these supply flexibilities, we can have flexibility from the demand side across various timescales. So demand shifting of electric mobility and heating, for example, can provide intraday flexibility, and the elasticity of fuel consumptions can provide flexibility in longer horizons. The part of flexibility that is not met domestically can be compensated by energy trades. So we have power trade and fuel import options, but these are involved with socio-political and also technical uncertainties. So this motivates our study, and specifically given these variety of flexibility options, what is a cost-effective portfolio to meet the needs for flexibility across timescales? And also considering the uncertainty of energy trade, what infrastructure investments should we make to secure the energy supply under limited power trades or fuel embargoes? So this leads to the objective of this research, where we examine the flexibility provision across intraday to seasonal timescales in the sector-coupled energy system of Switzerland under various energy trade scenarios. So we conducted this research in PATHFNDR Work Package 1 in a fruitful collaboration between RRE and the Energy Science Center. And we promoted the state of the art in the literature by employing a high spatial temporal resolution and also a thorough flexibility representation. Okay, so I'll continue this presentation with an overview of the methodology and split the results in 3 sections and finally conclude with some takeaways. So we look at 2050 and optimize the investments and hourly operations. We use Nexus E to model the power network of Switzerland and neighboring countries, and also use GasNet to model the gas network. And we look at the interface of these 2 networks with power to power technologies and gaseous storages. So we select 14 locations you see on the maps. Some of these locations are in the Aare Massif, which has the potential to install caverns. Okay, with this, I want to continue with the results. The first result section looks at the operations under reference energy trades. So we have the flexibility on both the generation side and demand side. And these seasonalities are contrasting, meaning that we have higher generation in summer and higher demand in winter. And several generation technologies can contribute to the winter supply mostly. These include reservoir hydro, alpine PV, biomass, and methane to power. I mean gas-fired power plants. And on the demand side, we see a relatively large contribution by pumped hydro and electrolyzer absorbing the excess renewable energy in summer. On top of that, we have the demand flexibility, which provides intraday shifting throughout the year. And what is remaining is compensated with net imports in winter and net exports in summer. So if we look at the gas side of things, we see that the seasonality in the power sector propagates. So we have the power to gas mainly happening in summer and methane to power mainly happening in winter. This adds to the already seasonal methane demand, and we end up with a highly seasonal total methane demand. So to address this flexibility on the hydrogen side, we mostly rely on imports, and to a lesser extent, we deploy hydrogen storages and utilize the demand flexibility. And on the methane side, similarly, we see that the domestic biomethane is providing seasonal flexibility. This is augmented by flexibility from fossil methane imports, you see in red, and also a relatively large amount of methane storage. Okay, now I want to see the operations of different technologies for storage and compare them. So we look at two hydro technologies and two gaseous storage technologies. If we plot the storage level over the year, we see that the storage level is minimum around March and maximum around October for all four technologies. But to reveal the operational differences, we do the following practice. So we start with the storage input and output. We draw the cumulative energy into the storage and out of the storage, and the difference between the two curves can give us an indication of how long we store energy. So with this, we can compute a storage curve like this, and we can understand where each storage technology is providing flexibility. In the case of pumped hydro and hydrogen storage, the average duration is around a month. And this is mainly driven by the variable renewable generation that is fluctuating along different timescales, especially multi-day. And if we look at the reservoir hydro, we see that the storage durations are around 2 months. And this is mainly driven by power demand fluctuations. And methane storage boasts the longest duration. And these fluctuations of methane demand and e-methane prices are the driving factor for this long storage duration. Okay, now let's explore how investments and operations change if we limit the energy trades. So we look at 4 scenarios. We start with the status quo, which is 2020, and we don't allow any new investments in this scenario. The next scenario is the base scenario, where we have the normal NTC and reference fuel prices, and we allow investments into tanks and caverns along other technologies. The lone scenario corresponds to the energy market integration dimension in cross scenarios, where we limit the power NTC to 30% of the normal value, and we do not allow any fuel imports. In addition, we introduce a variant, which we call without LRC. In this scenario, the only difference is that we don't allow investment into line rock caverns to see the impact if they don't prove physically or technically feasible in Switzerland. Okay, let's focus on the power sector results first. So first of all, we see that there is a need for a high expansion of renewable energy capacity in Switzerland. We see it along all the scenarios for 2050. But this is more drastic in the scenarios where we don't allow as much as we want of energy trades. So in these two scenarios, the lone scenarios where we don't allow power imports and also fuel imports as much as we want, we see higher renewable deployment, especially wind. But this higher renewable installation with under limited energy trades leads to higher curtailment of renewable energy. And the important thing to notice here is that in these lone scenarios, we don't invest in like power generation from gaseous fuels, be it methane to power or hydrogen to power. This suggests that the domestically produced fuels are not viable for power generation. They are too costly for this purpose. Now looking at the gas side of results. So we see an emerging hydrogen demand in 2050. So in the base scenario, it is supplied by a combination of domestic resources and imports. But if we don't allow imports, we tend to produce as much as we can from domestic resources. And especially electrolyzers can realize this using the excess power in summer that cannot be exported to produce fuels that are used domestically. If you look at the methane supply, the first thing that we notice is the drastic reduction in fossil methane imports. And this is driven by the emission limits. The next thing that we notice is the shift from imports to domestic resources like biomethane and e-methane, that is electricity-based methane, when we do not allow fuel imports. And if we look at the storage sizes, we see that up to 1.7 terawatt of cavern storage would be used to ensure winter supply in the year 2050. But if we exclude storages, so we end up with only 0.2 terawatt hours. This implies that tank storages are not economically viable for large-scale storage of gas or hydrogen. Now I want to talk a bit about flexibility from the demand side, especially looking at hydrogen and methane demands. In the base scenario where we can import as much as we want, or at least under normal conditions, there is little contribution from the demand side. But if you look at the lone scenario, we see that the contributions increase, especially along seasonal and annual timescales. And this indicates a demand reduction, especially in winter. What if we go to the next scenario where we don't allow fuel storage? Under this scenario, the contributions increase to above 6%. It means that almost 6% of demand is reduced overall throughout the year due to increase in the costs. So this concludes this section of the results. Now that we have seen that import conditions influence the results very much, we want to do a more extensive analysis of a broader trade trade scenarios. So specifically, we look at the role of hydrogen and methane technologies across these scenarios. So we start with 4 prices that we define for importing hydrogen and e-methane, and then combine it with different levels of net transfer capacity. We end up with 16 scenarios. The base scenario is here, where we have the reference import prices and an NTC of 100%. So let's dive into the results. Let's focus on the conversion technologies between power and methane and hydrogen at first. So hydrogen to power, we see that it supplies mostly in winter and only when import prices of hydrogen are below 70 euros per megawatt hour. So little contribution along the scenarios. Whereas methane to power is more important where we have limited NTC and we tend to use imported fossil methane combined with carbon capture and storage to fill a part of the winter supply gap. And if we look at the power to hydrogen portfolio, we see the contribution is mostly in summer. Specifically, if we have costly imports, we tend to produce hydrogen domestically. And if we have limited exports that we cannot use you cannot use power to export it to neighboring countries, then you tend to use this power for domestic uses. That's why we see a higher contribution under lower NTCs. And power to methane follows a similar trend. We have the maximum deployment in lower NTCs and also when it's more costly to import e-methane. And finally, let's take a look at the storage deployment in these scenarios. So we see up to 6 terawatt-hour of hydrogen storage is deployed, especially in this costly scenario. So we import hydrogen, or we deploy this hydrogen storage to avoid the costly imports in winter. So we transfer the production from summer to winter using this seasonal storage. And for methane storage, we see up to 1.2 terawatt-hour of storage deployment, especially when the import price exceeds 150 euros per megawatt hour. It's important to note that when there is a trade-off between the 2 storage types, like when we go through the power to methane pathway, we tend to use methane storage. So we store the final methane rather than the intermediate hydrogen. It's simply because methane storage is less expensive. So now that we have looked at the results with some depth, I want to derive some conclusions and share some insights with you. We have compared our results with the literature and relevant studies in Switzerland to make them more robust. But at the same time, I will present quantities from our main scenarios so that we have a better understanding of where we stand. Okay, we need a significant expansion of PV, wind, and run-of-river by 2050. This is almost 7 times of values of today. If we limit power exports, we're at the same time introducing more renewable curtailments. We see that power to gas often runs on excess power in summer. But it's important to note that even when we cannot import fuels and we cannot export power as much as we want, the total contribution of power to gas is less than 13% of the total overall power demand. We see that gas turbines burn imported fuels rather than domestically produced ones, and their contribution is mainly to supply power in winter. Additionally, we see that fuel embargo reduces final gas demand by something like 5% in winter. Fuel embargo additionally results in higher installation of gaseous storages, as we can compare the two scenarios. And at the same time, it increases the storage durations, so more seasonal operation of storages. Regarding the spatial results of our models, because it's a strength of our models, we find that where we can install caverns play a crucial role on where we can really install storages and power to gas. Additionally, we see that power network constraints and network capacities play an influential role on the placement of power generation, power to gas technologies, and where we expand the power network. So looking ahead, we envisage 3 directions to follow this research. First, we want to align with cross scenarios as much as we can. Second, we want to use EuroCalIP, a European energy system model, to obtain some boundary conditions which we currently derive from exogenous sources. And finally, we want to identify the impactful parameters so that we can conduct and further do a sensitivity analysis. So last but not least, I want to thank my supervisor, Professor Sansavini, and my collaborators, Jared and Elena, with their invaluable contributions. And with this, I thank you all for your attention and open the floor for any questions you may have.